Okay, everybody, how's it going? All right, welcome to session 19. This session is the last one for which you will be responsible on the exam. And I can essentially assure you that you will have at least one question on it, okay? We're going to cover Mohr's circle today, which essentially is a rite of passage. So I'm privileged to be able to be one of the first people to share this with you. Have any of you used Mohr's circle in the past? Anyone? Have you heard of it? Have you heard your upper classmates say, "Oh, Mohr's circle"? Okay. All right. So it's going to be I hope that will present it in a way that it does it justice and that you also get something out of it. Administratively, we have the exam a week from today. I have people's exams. If you did not pick up your exam and you would like to, I understand if you don't want to, that's fine. But if you didn't take a photo of your previous formula sheet or your note sheet, you might want to pick that up at least. Okay, and for this next exam, you get to bring in 2 sheets, okay, front and back, all 6 sides, all 12 sides. All right, any questions on that? Okay, good. So we have the opportunity to try to get this to work. Yes, to derive Mohr's circle today, to discuss quite a bit about how to go and think about constructing Mohr's circle, and also attempt to then map Mohr's circle to some of the structures that we've been looking at in the past. Okay. And first, though, just kind of a review, this is our 3rd session on plane stress. So session 17 is where we introduce the idea of using sections on a material element, coming up with a new triangle, and performing equilibrium. And again, please be able to do that a week from today, showing your work using equilibrium. We also described the general form for equations of stress transformation in 2D. These are very good to write on your notes that you'll bring in. If you're really, proactive, I don't think it's the best use of time after what we're going to discuss today with Mohr's circle. But if you wanted to, you could program these in your calculator, and you could put in sigma x, sigma y, tau xy, and boom, and an angle, of course, and it would tell you things. I don't know. It's probably not the best use of time, but you could do that. And we've done a lot of this in the last assignment in Python, where you kind of use this trial and error method. It's not really completely random, right? We're putting in ranges of angles between 0 and 180 degrees, and we're looking at the resulting sigma x prime, sigma y prime, and tau x prime, y prime. We also have discussed how to, well, that's interesting. I don't know, that's very interesting. I don't know what happened there. But we've also discussed how we can take the derivative of those prior transformation equations, set it equal to 0, and find the maxima or minima. And that's useful because we're interested in understanding when we are in a state of principal stresses, or if we're in a state of maximum in-plane shear stress. And this is just how to calculate maximum in-plane shear stress. Any questions on what we've covered up to this point? because we're going to build on it. If you have, did anyone find thinking about pure shear interesting? I don't know, right? Where you have this state where you have just shear stress, you can get a state of maximum in plane shear stress with no normal stresses. And then what happens with the normal stresses when you rotate 45 degrees? Anyone remember? So we have a state of, recollection time, right? So let's say that you have a state of, and this is x, this is y, those are not stresses. This is tau xy. So that's a state of pure shear, right? Any recollection on how to figure out what the principal stress is here? So if this is pure shear, which is a state of maximum in-plane shear stress. How do we get to principal stresses? Any recollections? Any ideas? Any comments? Tell me what to do. Yes?
You find the angle where the tau xy prime is going to be 0.
Okay, so that's one way to do it. So we could find all right, so that's one way to do it. Other ideas? That's not a bad way to do it. Yes.
Since you know, like the state of the angle at which the maximum shear stresses, you know that the principal stress is at 45 degrees.
Right. Okay. So that's probably a good approach, right? So I can draw. Ooh, that was more distorted than I want. I'm trying to draw that. Okay. Or should I be drawing it another way? If I'm taking this element, actually, maybe I should draw it another way, because if I have it at like this, and I have these shear stresses, okay, going in these directions, okay, what's going to be happening to my my element, right? So it's kind of like shearing it so that I've got, maybe I've got a little bit of that, a little bit of that, a little bit of that on it. Okay. That's kind of another way to think about what's happening to this element. So you could kind of say, oh, it's maybe getting pulled a little bit more in this direction. Whoops, I made a boo-boo. No, someone was going to tell me I made a boo-boo, right? So it's getting pulled a little bit more in this direction. So you can kind of say, oh, maybe there's a normal stress in that direction that's going that way, and maybe there's a compressive stress like that. Can you kind of see that? We haven't done any math, right? What we're looking at is what is a 45-degree transformation look like on a rotated element. Because that state of stress is still present. Okay. So what we can say is that this would be a new sigma 1, and this would be a new sigma 2, and we know that sigma 1 is equal to minus sigma 2. Okay. And today, with Mohr's circle, it'll be very quick to figure out what those magnitudes and what those signs of the sigma 1 and the sigma 2 might be. Okay? But this is 45 degree rotation. Okay. We're just using kind of the thinking about this approach. Okay? Not doing the math yet, just thinking about what's happening. And then, of course, if we use the equations or we use the equilibrium triangles, we can figure out what those values are going to be, okay, from the state of pure shear. And it turns out that since this is pure shear, sigma 1 will actually equal the original tau xy. Okay, and the minus tau xy will be sigma 2. Okay? All right, so just be familiar with that. If you look at some of the prior exams also, you will find that sometimes we play a little bit of a game when we have a state of stress, and it'll be more, we'll talk about this more today, where we have sigma 1, like that. I hope we'll get to it today. We'll see. So in this case, what structure has this state of plane stress? Where you have sigma 1, or sigma x equals sigma 1, sigma y equals sigma 1, and tau xy is equal to 0. What structure is that? Yes. Yeah, which one? Which one? Yes, which one? Yeah, thin-walled, good. All right. You have two types, right? Take a guess. The two types being spherical and cylindrical. Yes, that makes, I mean, even if you didn't know anything, right? You're like, oh, that thing is completely symmetric, right? So yes, this would be a state of stress that you have in a spherical pressure vessel. Okay. Where the sigma 1 and the sigma 2 are PR over 2T. Okay. But think about what happens with rotation. And we'll just leave it as an open-ended question. And maybe we'll get back to it today. But definitely think about it before Tuesday. All right, so new material. Otto Mohr, Christian Otto Mohr, okay? German professor, made contributions to structural mechanics, wrote a book, published some papers. He retired in, well, I don't know when he was born, but I know that he retired in 1900 and he died in 1918, a la Wikipedia. Okay, he I guess made contributions to indeterminate static systems. So yay, right? We love those. And he appreciated graphical approaches. He's not necessarily the one that came up with this graphical approach initially. It was maybe someone else, Clausen or something, but he's the one that kind of pushed the idea that we could use this technique to kind of quickly come up with responses or understanding for transformations. So these diagrams on the left should already be familiar, and this one, this one right here with this equation for radius and a bunch of and a sigma average, all these things will be clear by the end of today. Okay? But so you don't worry about drawing it down. We're going to draw these lots of times. It's just to say this is what he did, and this is what we're going to do today. Now, the derivation is not that complicated, really. you start with the two equations for transformation for sigma x to sigma x prime and tau xy to tau x prime y prime. Okay, so remember these? These are the equations that we essentially got straight out of doing equilibrium on a method with a method of slices on a material element. Oh, and yes, I'm sorry, I have to make a, I'm sorry, I forgot. I promised someone that I would show the attendance. So this is completely disrupting the flow, but let's go ahead and do this. I'll show it again at the end, so don't worry. But if you've got to go somewhere, I understand. I think though you wanna tune in to me or someone else to be able to understand these concepts though. And is it gonna work? All right. So go for it. Oh no, what happened? That's weird. That is strange. It's not my computer. I don't know why it does that. All right. We're all good? Almost all good? Okay. Please upload it. I know it'd be nice to have a class at the end where we didn't have requests and things because they were uploaded. Okay, so let's get back to what we were doing. All right. So we start with these two equations, and then we go ahead and we square them. Okay. After we've made this one the top one like this. So you square both of these, and we add them to each other. Okay. That may look kind of messy, and it is a little bit of a mess. All right. But this expression that we see here, this equality that we see here, can be written as follows. It can be simplified, right? And you see that we've got some, you've got some cosine squareds and some sine squareds, right? And cosine squared plus sine squared is going to be equal to 1. So that helps us out a little bit. This expression right here, okay, is going to describe an x-axis, okay, and this expression right here is going to describe an offset. This expression right here is going to describe the y-axis with tau. Okay, that's the offset coming in. And this expression on the right is a radius. Okay. So you're going to have this average expression being important, and we're going to have this expression on the right being important as a radius. And we're going to have a center of a circle at sigma average 0. So what in the world are we talking about? Is it pre-calc? No, it's probably algebra 2. Where in your math do you first learn about the equation for a circle? Algebra 2, is it? Okay. And what is the equation for a circle? At the origin, nonetheless. Just give me the equation for a circle of radius r at the origin of an xy coordinate system. Huh? Okay, close. There's an x squared, there's an r squared. What else does there need to be if I have an x and a y? So there's an x squared, there's a y squared, and there's an r squared, right? Yeah, so you remember that for a circle, at the origin, something like this, if I have radius r, it was just x squared plus y squared equals r squared, right? And if I wanted to move the center left or right, what did I do? Yes.
You have to do like the x plus the new the v in displacement in the x direction squared plus the y in displacement in the y direction squared.
Right. So remember, let's say that I wanted now this circle. Okay, and this is x, this is y, and this is the center. Right? You remember something like if they said, okay, that's some distance a. Okay, and so and I'm not moving it in the vertical, so I still have plus y squared equals r squared. What do I put before that plus sign? Yes.
X minus a squared.
That's right. It's x minus a squared. Okay? Now, what does that have to do with what we just did? What we're trying to state here, and we're going to do this a lot, don't worry. What we're trying to state is this right here, this sigma x plus sigma y over 2, that is the A. Sigma x in here, prime, that is the x. And tau x prime y prime is the y. And this quantity sigma x minus sigma y over 2 squared plus tau x y squared is the r. Okay, do you see that? No, what, or you just don't like it? You cannot like it, but do you see it? Or not? What do we map? Yes, Brennan. Sorry. Yes, this is the radius squared. So we have to take the square. So r is going to be equal, there we go, to the square root of that thing. Okay? Can we kind of see this? No, yes, no. Are you disappointed that we have to go back to Algebra 2? Are you happy? It's like, oh, Algebra 2 is useful. Okay. Yeah. So, I don't know, then when you started thinking about sine and cosine, you did that in Algebra 2 as well, right? Okay, so that's good. I don't know, I thought that was all pre-calculus stuff, but I guess I don't know. I guess you do it again in pre-calc, right? Because you introduce, where do you introduce trigonometric identities? Pre-calc. So, okay, all right. So anyway, we're going to be, this was maybe a little pre-calculus that I skipped, all right, to get from this line to down to this line, all right. But if you want to take the time, you can. All right. So the center of the circle again is going to be at this x offset, the average, okay, comma 0, and r squared is there. Now, here's a little bit more. We have these two equations. Okay, this is the sigma x prime minus the sigma average now, plus the tau squared x prime y squared, tau x prime y prime squared is equal to r squared, and the r squared is this. So, if you were thinking about a problem that you're given, usually you're given what? You're usually given the state of stress on an element, correct? So you would usually be given, what? Sigma x, sigma y, and tau xy. And often, right, what we're interested in figuring out is the sigma x prime, the sigma y prime, and the tau x prime y prime. Okay? So often these circles get drawn using the sigma x, the sigma y, and the tau xy. Right? You can see that if I know the sigma x, sigma y, and tau xy, I can put in an r. I can figure out what r squared is, and I can figure out what the offset is. So you can draw the Mohr circle. Now, I might have. We'll keep going. We'll keep going. I haven't really talked about what the axes are yet. Okay. But here they are. Normally, right, what we had before was x and y for our coordinate system, right? When we were just, not this coordinate system, talking about just Cartesian. Well, they're both Cartesian. The pre-calc x and y, all right? The algebra 2 x and y, right? When we had x minus a squared plus y squared equals r squared, right? But here, this horizontal axis is going to be what we call sigma, and that's related to the sigma x prime. Okay? But we just call it sigma. The y-axis is related to the tau, and we'll go into this in more detail. Hibbler, we're going to follow a convention. Okay? We're getting together, some smart people got together. Not actually, I don't know if it was a convention on the conventions, right? More like people just published, this is a nice way to do it, and some people did it this way, and some people followed other conventions. Once again, if I go back, I think to my time, no, I don't. Well, let's put it this way: the book that I used to teach design and mechanical components, they don't follow this convention. All right, they put tau going up instead of tau going down. All right, and in a slide or two, I'll get into why it's nice that this. Actually, the next slide, I think, we'll get into why it's nice to have tau going down. But the point is, the center is at the sigma. See this? This is the sigma average right there. Okay. Don't worry too much about this yet. We'll talk about that. You see the radius, okay, of this circle, right, like that, and we see that we have a sigma and a tau. So, why, or how are we depicting Mohr circle? Okay, we're going to use the convention number 2 here, and this is not like, don't go around saying, oh yeah, we use Mohr circle convention number 2. People are like, what? No, this is just the second convention that's been put in this figure. Okay, do you see what happens here? Is we say that tau is going down. So if you look at this plot, or if you look at this figure, 1 and 3 are not what we do because you see that tau is going up in those cases. And when we get to it, the rotation that we see in the Mohr circle of 2 theta, and we'll get to that. You've already seen 2 thetas, right? Where were the 2 thetas? They were in the sine 2 theta and cosine 2 theta for your transformation equations. It ends up being counterclockwise. If you do tau downward and you follow this theta stress, which is the theta stress we're following, then if tau is upward, then the 2 theta angle is going to be clockwise, so it's opposite direction. Or if you follow this convention down here, where they're saying that this is negative tau xy, okay, and this is positive tau xy here, and it's the opposite of what we do for our tau xy, then you can go the same direction and have tau upward, right? But this is mostly for your good to know file. When you're talking to other people, they may draw a Mohr circle in the opposite orientation, or they may do it they may have some other convention they're following. If they stick to their convention, and if we stick to our convention, we will get the same answers. Okay? It's just like beam bending, the V's and the M's. Okay? If you start to mix up the conventions, right, then we start to have issues. So let's take a look at a question here. And I think this may be one of the first ones on the homework. Okay. And let's just do a couple of things here. So at this point, so the question is, if an element has sigma x equal 100 megapascals, sigma y equals 50 megapascals, and tau xy equals 10 megapascals, what are the coordinates for the center of Mohr's circle, And what is the radius of Mohr's circle? Okay, well, we just said that the center. Well, you tell me, what's the center at for the Mohr circle? This is just to get us kind of excited. Yes. So the x-coordinate is going to be average, and the y-coordinate is going to be 0, right? So the center is going to be at sigma average, comma, 0. Okay, that's just what we showed in the derivation. So that's the first. Okay, what is sigma average? Well, sigma average is just sigma x plus sigma y divided by 2. Okay. And the other question is, what's the radius? Okay, the radius was a little bit. How do you say it? Was a little bit larger equation. Okay, but the radius we can write is going to be the square root of the difference of sigma x and sigma y squared over 2, or actually, okay, I better be careful. Yeah, let me just draw, I could put 4, okay, but let's do it this way. Sigma x minus sigma y over 2 squared plus tau xy squared. Okay, so it's just to kind of get us cooking here. We see they give us a sigma x, they give us a sigma y, they give us tau xy. We can calculate the radius and the location of Mohr's circle. So let's do it. The average of 150 is 75, correct? So sigma average, that's just 75 megapascals. This one is a little bit, the radius is a little trickier, right? So we'll write it out and then I'll just tell you what the number is, but it's going to be the 100 megapascals minus the 50 megapascals over 2 squared plus, what is tau xy? It's 10, so this will be 100 megapascals, like this. So this comes out to be a radius of 27 megapascals. Okay. So if I'm going to draw the Mohr circle now, I'm careful. I draw sigma on the x-axis, and I draw tau going downward. I draw a center here. We'll call that 75, 0, and I can draw a radius. It doesn't really matter right now where I put the radius, that radial vector, like that. Okay. So that's the basic idea. And we derived it. We derived it, right? This is the equation that we got. Maybe it's a little bit weird to be thinking about a sigma and a tau as your axes, but that's how you go. If someone gives you a state of stress on an interview, you can at least draw the circle. You get halfway there. What you do with that circle will probably make the difference, though, and we'll talk about what we do with it. Any questions up to this point? All good? All right. So, now, let's talk about how we're going to construct Mohr's circle. And you can already see there are a lot of details. There are many details. You know, what is this sigma y negative tau x prime? What is this sigma x prime, tau x prime, y prime? We got sigma x. You know, the sigma average we already calculated. We got tau xy. We got a 2 theta p. We got a 2 theta s, right? There are a lot of details that we got to cover in terms of how we use Mohr's circle. And, you know, we're going from here's a structure with a state of stress to an element or to the circle to a transformation. Okay, so this is a transformed x prime, y prime, you know, at some angle. And that's what we're ultimately wanting to use the circle to do. remember, tensors, or a description of stress, as it rotates, it preserves this information. Okay? So one way to think of what is observed, radius does not change as we do these transformations. Okay? The center of the circle does not move. Okay? Those things are fixed. So what happens, it's kind of like, when you were learning the unit circle and you had to go around the circle with different angles and things, right? You didn't move that circle. That circle stayed put. You could change the radius, but it would no longer be the unit circle. Right? It would be something times the unit circle. Okay. So what can we do with Mohr's circle? And this is just me telling you what you can do, okay? And we'll get there. We can find stresses in an arbitrary orientation. So rotating by 2 theta on Mohr's circle in the same direction as the orientation. So remember, we already had those 2 thetas and the cosines and the sines for the stress transformation equations. So what's going to be interesting is if you want to rotate your material element, this is pretty key, by some amount theta, we rotate Mohr's circle by twice that. And you remember when we were doing these plots, what do we say? The plots of angle rotation versus the sigma x prime, the sigma y prime, and the tau x prime y prime. Remember, we only went from 0 to 180 degrees. Okay? But that 2 theta, right, we said that's going to cover the 360 degrees. And so the Mohr circle manifests this property as well. So what might happen, okay, is we start with our Mohr circle. So here's Mohr's circle. And when we have a state of stress, and we'll go through this more, that state of stress is what we call location P. And that state of stress is given by sigma x, sigma y. All right, or sigma x, sorry, tau xy. All right, so location P, I don't think I have it on here, but see this location P right here? That location P is the starting, or is the state of stress with sigma x and tau x y. Okay, that might have gotten a little bit jumbled up, but do you see we have a sigma axis and we have a tau axis? Okay. And so the sigma axis we're going to use initially to map sigma x to location and a tau xy to that location. And that location is going to be on Mohr's circle. And if tau xy is positive, it's going to be a location below the horizontal. Okay, because this is positive tau going downward. Now, we would have already drawn the Mohr circle, and some interesting things happen. If you go 180 degrees, that's like going 90 degrees on the material element. And so if you went 90 degrees on the element, you would go 180 degrees like this, right? You see these poor lines are supposed to be collinear. This one right here and this one right here are supposed to be collinear. If you go all the way around, 90 degrees from sigma x, okay, is sigma y. Right? We've now done this. We've rotated an element. Remember, if you watch some of the videos, it was like, okay, look, we do this transformation, but then if we go another 90 degrees, sigma x prime becomes, or sigma y prime becomes sigma x prime 2, and then you have sigma y prime 2 out on the other side, 180 degrees off of sigma x. Okay? So, or sigma x prime, sorry, right? So what we're saying on here is that we can depict the state of stress. And then we can go about and we can figure out how a rotation on the material element affects a new location on Mohr's circle. This new location right here, for example, would be what we consider to be a P prime, which is related to sigma x prime, tau x prime, y prime. And it's with a rotation of 2 theta. So now the new state of stress is going to be along or depicted by this point on this side and then 180 degrees at the other side, the sigma y prime, and the minus tau x prime y prime. Remember also, when we went 90 degrees with the shear stress, or we rotated 90 degrees, like a tau xy would become a negative tau xy. Okay, so that's also what's happening when you go from here to here, when you go across the circle. Going across the circle is like rotating 90 degrees. The material 90, going across is that 2 theta equals 180 degrees, and that is equal to theta equals 90 degrees, and that's rotating the element 90 degrees. What else can we do in Mohr's circle? We can find the principal stresses. What's the definition of principal stresses? A state of principal stress? Yes, Mark? Shear is equal to 0, okay. And what else? Well, shear is equal to 0 is a good one, right? What else? Yeah, Mark?
It's like maximum normal stress.
Yeah, so you're going to get your maximum normal stress, one of them, and your minimum normal stress, and you're going to get 0 shear stress, like you said. Where would you find the principal stresses here? Yes?
On the sigma axis.
Yeah, right? On the sigma axis here, right? And so you're rotating to get what? To get this to be here and that to be here. And the shear stress is 0, right? That's what you're getting at, Mark. Yes, Michael.
So is it correct to say that at those 2 places where the tau x prime y prime is 0, that even though one of them is on one side of the circle, the other one is on the other side of the circle, they're both considered maximum
So
for the normal?
for the normal, so they are, yeah, you're getting the, you're getting to them being at their maximum difference from each other, okay? And yes, if, this one out here is definitely the, kind of like the largest of the two, the larger of the two, right, for in-plane stress, okay? Okay, yes, you're pointing. Do you have a question or observation? Do you have an observation that you want to share? No, you're thinking. So what are you thinking about? No, if you have the question, or if your buddy has the question, I honestly want to hear what the question is.
Like I understand that when P is sigma x and then T is y, and then mirror opposite to is sigma y. That's all it does.
Yes, that's right. And is it T or is it tau? Yes, we're going to the Greek. I'm not Greek, okay, but yeah. So we're going to the tau, okay. What else do you think we could find? Da 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 da. Hold on, it's not da 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 da. We can also find the maximum in-plane shear stress. So where is that going to be? Yes. Say that what?
Tau axis.
Okay, it's going to be, yes, so we're going to be looking at the tau axis, that's true. Where is the maximum going to be? Remember, you cannot leave the Mohr circle. You must be on the Mohr circle. You cannot move the Mohr circle, you cannot change the radius of the Mohr circle, unless you change the magnitude of the loads. So where would it be? Yeah.
Power retrieved from the horizontal.
Yeah, so it's going to be up here and down here, right? This is going to be the negative, the maximum negative of it, and this is going to be the maximum of it. Are these magnitudes, are these distances the same? Yes, because it's a radius, right? Describing the circle, right? So that orientation is where you find the tau max. What can you see about the sigmas there? Yes?
Average.
That's the average, right? That's the average. Okay? And so there is that case, right, where, well, I won't jump there yet. Well, I'll just finish my thought and then we'll come back to it, right? Imagine that this was at the origin where sigma average is equal to 0. Okay? You can have, that would mean that you have a state of shear stress without any normal stresses. And what is that called? That's called pure shear. Right? That's called pure shear. Okay? Let's see. Let's do an example then. All right. So example here is if an element has sigma x equals 100 megapascals, sigma y equals 50 megapascals, and tau xy equals 10 megapascals, and we rotate the element 30 degrees counterclockwise, what are the resulting sigma x prime, sigma y prime, and tau x prime y prime? Okay. So we start with an element that looks like an element. Okay, with our sigma x or sigma y or tau xy. And then they say, and then I said, we're going to rotate 30 degrees. So we're going to rotate this element theta equals 30 degrees. So we're going to draw our sigma and our tau axes, like so, and make sure that tau goes downward to follow our convention. We're going to plot the center of the circle, which is just the average. So right there, sigma average, sigma x plus sigma y over 2. We're going to plot the reference point P, sigma x, tau xy. Okay, so that comes over here, like such. Okay. And we can say that that's going to be 100, and it's going to be the tau xy 10, like that. All right, that's the point P. The x, all right, is given as such, and the tau is given from the distance from the horizontal. Okay, so that's how we got that. We can figure out the length of the radius. All right, so we have that fancy dancy equation, right, for the radius. But you tell me, using geometry, how would you find the radius? Yes.
Since we know what P is, can we do Pythagoras theorem to cause radius?
That's right, right? So we know P and we know the center, right? And so we know this is essentially the x squared plus the y squared equals r squared. Wait a second, that's the equation for the circle again. Huh, Pythagorean theorem, he had something. Pythagoras, right? So exactly, so often what happens is you don't use that equation, you use your geometry, okay, to figure out what r is. The only thing, well, there are multiple things you need to know, but you can, if you know the process, you know that the center is at sigma average, you know, that's sigma x plus sigma y divided by 2, of course, right? And you know that the point you're plotting is, well, going to be sigma x comma tau xy. You can kind of do everything else. And that's part of the beauty of Mohr circle, is that it's a graphical depiction of these somewhat messy equations for transformation, and also even somewhat messier slicing and dicing and doing equilibrium. Okay. So we can figure out what the radius is, and that it can be done by looking at, okay, this is 25 here, because I know that I have 100 minus the sigma average, right? That would give me this component here, that's the 25. And I have this component here, that's vertical, that's just tau xy, so that's simple. And r is then going to be the square root of 25 squared plus 10 squared, which is 27 megapascals. Okay. Now, we have to rotate by 2 theta on Mohr's circle in the same direction as the orientation of this rotation. So theta was equal to 30 degrees, which means that we have to go 60 degrees. Okay. Now, is this really a 45-degree angle like I've drawn? Not really, right? It's 25 in this direction and it's 10 in this direction, right? So if I want to know that angle that I started at, right, I can do the arctangent of 10 over 25. Okay. But either way, I can just right now put out that this, I'm going to go 2 theta, and I'm going to get to my new p prime. Okay, and it's going to be sigma x prime tau x prime y prime, like this. So the arctangent of this phi, I'm calling it, it's really the arctangent of 2 theta, you could say, right? The phi is equal to 2 theta, all right, but I just think in terms of a triangle. That's going to be 21.8 degrees. So I didn't draw this, super great. But I drew it so I could fit all my variables in it. So that's nice, right? Here, it's not as important. I know we use the exaggerated triangles when we were doing in the equilibrium. Here, it's not as important to do things exaggerated. But it is important to keep track of, is it, the 2 thetas. That's important, okay? So 2 theta is going to be 60 degrees. So we're going to go I'm calling it gamma. That's not necessarily the bestest, but again, we're going, because we've got 21.8 plus 38.2 has to equal 60 degrees. Okay? So that's where we're going. And then once I've got this gamma in there, I can say, I know r. R did not change. So r cosine, right, would give me what? The new sigma x prime minus sigma average. Sigma average didn't change as well. That's going to give me this distance here. Okay, you see that? And so sigma x prime is equal to 96 megapascals. Tau x prime y prime is just the minus, because this is now tau is we're in the negative side, so it's going to be minus r sine this gamma, okay, like this, and that's going to be then minus 16.7 megapascals. And this is just saying, oh, hey, Q sigma y was originally minus tau, and now I'm out here at sigma y prime, comma tau x prime y prime, and so the sigma y prime, okay, because this is the sigma is the horizontal axis, so that's going to be sigma average, okay, minus this distance will give us sigma y prime. So that becomes out to 54 megapascals. Questions? Maybe I sped it up a little bit. Yes? Say that again, is sigma y prime left to the center? Ha, good question. Good question. Okay. So sigma x is to the right of the center because I made sigma x larger than sigma y. If I had flipped this, if sigma x were to be 50 megapascals and sigma y were to be 100 megapascals, then my starting point would be somewhere out in this region. Does that make sense? So then I would have not what you just said, right? Because what would happen, the sigma average would not have changed. The sigma average would still be at 75 megapascals, but 50 is less than sigma average, so I got to start over there. Okay, good question. All right. And that kind of stuff gets confusing very quickly, right? What happens when you have a negative tau xy? well then your negative, you start out above the horizontal axis, right? So figuring out where that initial P is sometimes a little bit tricky. And of course, if you get that not quite right on the first shot, that's going to make, other problems happen. Okay, let's take a look at another example. Okay, here it's just already done for us. Here we have sigma x is 100 megapascals, and sigma y is 50 megapascals, and tau xy is 10 megapascals. Well, that's remarkably familiar. Okay, and now the question is, what are principal stresses and relative orientation? Okay, so I copied exactly what we just had, right, back here. Except now, so this problem was about figuring out, using Mohr's circle to figure out an arbitrary new state of stress. And arguably, in today's age with a computer, it's easier to punch things into a calculator, all right? All right? So that I can say, okay, would I use Mohr's circle for that, for figuring out arbitrary? I can. I just showed you how to. But don't do it unless I say you have to do it, all right? But when it comes to finding principal stresses and it comes to finding maximum in-plane shear stress, there's not a faster way that I know, okay? Now, orientation, yeah, you can punch that. You might want to punch it into a calculator for that, okay? But just often, like in DMC, when you take design of mechanical components, at least, well, if I were teaching it, it would be different if you're taking it with someone else probably. But we often, in that class, we don't really say, hey, tell me the angle of rotation you have to get there. We just care about what those values are more than we care about, oh, I had to rotate 28.1 degrees or something like that to get there. Okay? Why? Because when we're looking at failure criteria, we want to be able to figure out, okay, what are the maximum principal stresses involved, or what are their differences, okay, for brittle materials, and for the ductile materials, we're interested in, oh, hey, what's the maximum shear stress? Note, today we are talking about maximum in-plane shear stress. We will soon talk about absolute maximum shear stress, okay? But that's not today. Okay? There is a reason for us to say maximum in-plane shear stress, because there's also something called an absolute maximum shear stress, which is not necessarily in the plane. So anyway, here, what's cool is that we know the radius, okay? So what is sigma 1? What is sigma 2? What are they going to be? We know the radius and we know the average. Okay? So the orientation, yes, that part is, the relative orientation is a little bit tedious. But the calculation of what sigma 1 and sigma 2 are is really fast, because it's just the sigma average plus the radius. The radius was 27 megapascals. The sigma average is 75 megapascals. So sigma 1 will be 102, right, megapascals, and I don't have it here. I'm sure it'll come up, but going the other direction, right, you're going to have like 23 or something like that. No, you're 27. Okay, I can do some math. All right, so no, I can't do any math. 75, what's 75 minus 27? 48, right? Okay. Okay, so we need to look at the horizontal axes, okay? And we can look at that angle of rotation, right? We said we need to get, remember, we already calculated out what it was. It was 21.8 degrees, this kind of phi, or the 2 theta p, right? That's what's going to be equal to 21.8. So theta p is just going to be equal to half of that, 10.9 degrees. And so just, again, This angle here on Mohr circle is in fact 21.8 degrees. No mistake. But if I went back over here and I drew the material element, the angle of rotation is only half of that. Please don't make the mistake that I make. Be better than I, okay? Don't, just make sure you got this, all right? This angles of rotation here, theta, angles of rotation here, 2 theta. Okay, so, and then the magnitude, sigma 1 average plus radius, like we said, that's 102. And then we said sigma 2 is going to be the sigma average minus r, and we said that was 48 megapascals. Any questions on this? This example highlights one of the benefits of using Mohr circle, all right? In that we can calculate principal stresses very quickly. Yes?
Okay, so if we're asked to find the second principal angle, would that just be 90 plus that?
Yeah, right? So it's going to be 180 degrees on Mohr circle, right? Or actually, sorry. We're here already, right? So yeah, we go 180 degrees, right? And so we're just over here, and that's plus 90, okay? Good. Okay, what, you're pointing again. What is the question? What is the discrepancy? I saw some pointings. Did you have a question?
Oh, no, you're asking about
Oh yeah, arctangent, right. Where did that come from? That's because this height is the tau xy is the 10, and the x is the sigma x minus the sigma average. Yes?
So can you explain why the angle for the Mohr circle is 2 theta and not just theta?
Yeah. Okay. If we go all the way back to the derivation, right? Do you remember when we squared the sigma x prime relationship and the tau x prime y prime relationship? And there were a bunch of sine of 2 thetas and cosines of 2 thetas in there? Essentially, yes. In order for us to be able to get to equivalent, and they dropped out when we did just the drawing of the Mohr circle. Okay? But in order to be able to move around the Mohr circle, we had to keep them in place. Good. Okay, so,
I'm sorry.
yes,
Just a-
Brennan,
go
yes,
back one.
yes.
If tau x, y in this example would be negative for whatever reason,
Yes.
we have to keep our tangent be different, or is it the same?
Yeah, you got to be careful about what you're doing, right? Because, so let's say that it was negative and we started here. Sometimes you want to keep your life simple. So what you're saying, like let's say that your P point is right there where the laser pointer is, right? I'm going to, if I want to get to my state of principal stresses, I actually want to apply a negative angle to go back down to here, right? Because that's the smallest rotation for me to get there, okay? So yeah, when you start looking at, so you'll do the arctan here, and you need to be careful, right, of what that angle is, what the 2 theta is, okay? But you're going to essentially say, yeah, it's a negative. I would say it's a negative. You could say it's, whatever. You could go around the circle the other way, or you can go around over to here, right? And you got to keep track, right? So if I go like, let's say that this is arbitrarily, this is 2 theta is equal to 45 degrees, right? So that means to get over here, I got to go 135 degrees, right? And that would be valid. But that 135 degree rotation on Mohr circle then is got to be divided by 2. The material element actually only experiences 67.5 degrees of rotation. Is that right? Did I do that right? Yes. Okay. So, yeah. So you're absolutely right. You got to, again, keep track of where you start, and you want to get. These are your. This is where you want to be for maximum, or for maximum normal stresses or principal stresses, and top and bottom is where you want to get for maximum in-plane shear stress. And you can figure out now. You can play. It's not a video game, right? But this is what they did before they had video games. Okay, well, a few people did that, right? Okay, so an element rotation of 90 degrees on Mohr's circle, all right, is going to give us, oh, sorry, yeah. Okay, sorry. We're rotating the element 90 degrees, and then on Mohr's circle, that's going to be a 180-degree rotation, okay? And we just kind of put this point out there here. So remember, if I started with sigma x here, then 90 degrees, sigma x prime is where, better said, the x prime direction is now where y was, okay? And the y prime direction now is in the negative x direction. Okay? So this would have been the x. Okay, and so we can see that that shifts the tau x prime y prime to be in this corner instead of this corner, right? Because this is now the x face, the x prime face is up, right? And just again putting all these things out, and the tau x prime y prime is going to be equal to minus tau x y. And Mohr's circle will tell us the same thing. If we start at some location, let's say here, and again, yes, I'm making. Often when you see these drawn with this convention, you're going to be like, okay, I typically try to put p in that bottom right, because that's where sigma x is greater than sigma average. Doesn't have to be that way, and tau xy is positive. Okay, but then if I go 180 degrees on Mohr's circle, right, I'm up here at when I have a minus tau xy, and I have sigma x prime, tau x prime y prime, like that. Okay, and that would have been what sigma y was. Okay. So again, just justifying this 180 degree line and how you can write. So I mean, one thing I said p is this, but there's no reason why you can't write sigma y comma minus tau xy to get started. Okay, like if the question was saying, hey, I know what I don't know if this is the greatest question, but I know where the center of Mohr's circle is. I know that I have a sigma y prime or a sigma y equal to this, and I know I have a tau xy equal to this. Tell me what sigma x is, right? Just playing around with the variables and the unknowns. So you would be able to figure out, oh, I got to go all the way to the other side, and I can figure out what I can figure out what the radius is, and I can then go over here and say sigma average plus, an r with this angle relative to this would give me where the sigma x is. Okay. We're going to go a little faster because we're running out of time. Okay, so there's a couple questions here that you get to do for fun and credit. Okay, a few actually that you get to do. Question 5, all right. And then part 3 is let's look at structures. Okay. And what are some structures? Well, they could be bars, they could be rods, they could be thin-walled pressure vessels, they can be beams, right? And we're going to have states of stress, right? You see how everything is intertwined. We did bars, rods, beams separately. Then we combined the loads, right? And we said, oh, at that location A, you can have a sigma x equals this and a tau xy equal to this, right? And now we're saying, oh, we can take those sigma x's and tau xy's and sigma y's, throw them into transformations to figure out where the principal stresses, or what the principal stresses might be, what orientation might correspond to that, and also what the maximum in-plane shear stresses might be, and what the orientation of the element would be there. Any questions on that? The class, so people have asked, hey, so exam 2 just covers from, the last exam to this exam. What do you think? Now, you still have to be able to figure out, like we're going to talk about right now, how to figure out, a normal stress and a shear stress from different geometries. So, we already, this is the same, this is copied slide. All right, these are the 3 things we can do. We can find stresses in an arbitrary orientation. Tedious. Find principal stresses. Much less tedious. Find maximum in-plane shear stress. again, very much less tedious. These 2 points are the biggies. Okay. So let's go now to uniaxial loading. You're like, what? We're going back to like session 2? Session whatever? Yes. All right. So what is the axial stress here, right? If we know the P, we know the A, it's just P over A. Now, this is uniaxial loading. So, what is the state of stress if I have X in that direction? Right? I need a coordinate system mapped to a structure now. So what's the state of stress? What are sigma x, sigma y, and tau xy? Yes?
Sigma x is p over a and 0 for the other two.
Yeah, and 0 for the other two, right? That is one solid depiction of stress. Uniaxial loading. I jumped a step. What did I do here? Why did I say sigma 1 equals P over A? What does it mean when I put a 1 there?
X direction.
Okay, sometimes it means X direction, yes, in FEA. Now, though, what else does it mean? Huh?
Maximum.
Yeah, it's a principal stress. Sigma 1 is a principal stress. Okay? So, sigma 2 and sigma 3 are equal to 0. Okay, so we talked about this a little bit, all right? And we'll definitely talk more about this on Friday, but it won't be, I guess, technically on the exam. Do we see this, though? The humble uniaxially loaded bar is in a state of principal stress, the way we draw it. Okay? Now, here is what we did. We used to write sigma x, now we're going to write sigma 1. But in FEA world, yes, we can write sigma 1 too. Sigma 1, not sigma 1 as well. All right, don't write sigma 1 too. That would be tau. Okay, you know what I mean. All right, so, and then that's the x, that's the y. On Mohr's circle, or what would Mohr's circle look like here? Where's the center of Mohr's circle? What's the radius of Mohr's circle? Yes.
Half of sigma 1.
Okay, so that's a double whammy, right? Which one are you answering?
Oh, I thought you said the center.
The center is half of sigma 1 comma 0, yes. And
What was the other question?
what's the radius?
Oh.
Also what you just said. Sigma 1 over 2, right? Yeah. Okay? So you see, this is going to be fun. We can write, it's out there at sigma 1, yes. We can write that the center is at, sigma average, sigma 1 over 2. All right? And we have, and we can also write that the radius is equal to the sigma average, which is equal to sigma 1 over 2. Okay? And if we want to describe now getting to tau max, so remember we have this beautiful depiction of principal stresses. And if I didn't have a question here, there's not really much said here, but the other type of important state is in plane, at least for now, the other type is in plane maximum shear stress. So that happens right down here when we get to minus up there, right? So what is tau max? Tau max is just going to be, well, it could be either minus sigma 1 over 2 if it's up here, or it could be tau max is equal to sigma 1 over 2, right? And this is where, like, I'm not always the best at keeping track, because in DMC world, we just like want to know the magnitude. Okay. But the maximum in-plane shear stress, yes, is going to be sigma 1 over 2 as well. So what does that look like? That means if we rotate 45 degrees, okay, in this world, we rotate 90 degrees in this world, okay, on Mohr's circle. What's this one? So in the real world, the material element rotates 45 degrees. On Mohr's circle, it rotates 90 degrees. Okay, and then we can draw that the state of shear stress, x prime, y prime, it's going to be that's backwards. Blast. Okay. Yeah, okay? Because see, we wrote, no, that's right. Shoot. No, that's right. I'm wrong. See, I even get confused. Or not even I just get straight up confused. Okay, what did I do wrong there in my brain? What's wrong with me? Well, hopefully not much, but my thinking, okay? Remember, this is an element that's been rotated 45 degrees, so we have to go up this direction. Okay? We go up to here because we're going in the same direction. So yes, the state of stress is going to be minus, okay? It's going to be minus the sigma 1 over 2. So this is a little bit. Let's just change this. This is not clear. Tau max is going to be a positive number, sigma 1 over 2, and the state of stress that we're getting to is going to be minus tau max up there. And so when we draw it, it's tau max positive, sigma 1 over 2, and so it's going to be, or it's tau max with the arrows in the opposite direction, like we see here, right? So if I had drawn the arrows meeting up here, that would mean that, and I had a positive value, that would mean that the tau max was, tau x prime y prime was actually positive. But since it's negative, it's up here. I flip the arrows and I draw tau max that way. I'm sorry. Maybe I'll be better the next time at describing it. Any questions on that? Okay, so we have described now the state of maximum in-plane shear stress. And this is important. Oh, sorry. We're almost done describing the state of maximum in-plane shear stress. There are also normal stresses, right? These values are going to give us the state of stress, sigma, either this is the sigma x or this is the sigma y. They're the same, it's just sigma average. And they're coming out of the faces like this, right? Because it's not over here. You can have situations where your sigmas will be negative, but they have to be on the left side, not on the right side. And pure shear is a good example of that, but this is not pure shear. This is uniaxial loading. Okay, pure shear is another case. I've got 3 minutes. I'll go through this quickly. Pure shear is from this example, would have x coming this direction with this coordinate system, and tau is going to be going up that direction. We've done this on homeworks. We've done this, I think, in class 2. And so we have those shear stresses as drawn. If we flip it just so that we're looking at our xy coordinate system like we normally do, especially when we do rotations, okay, we can draw pure shear like that. We can map the tau xy in this situation to the tc over j. And we can then draw a Mohr circle using the equations that we have. Sigma average is equal to 0 because there's 0 sigma x and 0 sigma y. And so what do we get? We get a Mohr circle where we just have 0 comma tau xy down here. And then this would be 0 comma minus tau xy up there. This is a sigma x. And this one up here would be the sigma y. And this is the tau max. Okay? Now, what does the state of principal stress look like? Well, we rotate 90 degrees on Mohr's circle to get to the horizontals. And so, look, sigma x prime is going to be positive. What is it going to be? It's going to be the same thing as tau max was, right? So it's going to be whatever this value was up here, and then sigma y prime is going to come down to here, and that's going to be minus that value. Okay, so the state of stress looks like this. Okay, and we draw it like so. Okay. In the state of principal stress, there's 0 shear. All right, we'll stop there. Thank you very much. I hope you feel like you've got an idea of how to use Mohr circle. This is something that you can commiserate and discuss with your fellow mechanical, civil, aerospace, whatever, biomechanical engineers. Have a good day. And I'll show the attendance again. Just give me a second.